You are a tool maker.
Yes, that's a pretty good definition of me.
And some of your friends are tool makers, and there's a whole tool making community for scientists and engineers, it seems like.
That's right. Scientists and engineers have a huge amount of need for software. A lot of it is stuff that everybody knows about, MATLAB, AutoCAD, Excel, whatever. But there's a community of people that I'm part of that's trying to take a different approach to a lot of these things. That's trying to answer questions relating to, how can we visualize things differently? How can we interact with things differently in such a way as to improve things in a very general way for our approach to interacting with data?
And what are the problems with the existing tools that you mentioned, like MATLAB, Excel? These are pretty powerful structures already, right?
Yeah, they're tremendously powerful. They require a huge amount of know-how in order to get to the point where you're using them. They are not very visual at all. You've got to be, in order to use something like MATLAB, you've got to be the kind of person who's very willing to take a thing that you're thinking about in a certain way, turn it into a bunch of symbols, and then interact with those symbols, see the output of those symbols, and then maybe you've got to turn it back into this and then back into this. And that's a skill that people do get very, very good at, which is great. And it's great that society computers are already making it so that we can interact with data and models better and better. But there are different ways that you might do it. There are more visual ways that you might do it. And these can potentially make things more accessible to more people and make it so that you have a more direct relationship with what you're doing with a data set.
Well, there's historically been a sense, maybe I'm wrong about this, but that it's the people who are able to do that kind of abstract thinking that are going to be the best at science in general, right?
Mm-hmm. That is true to a large extent.
Like quantitatively minded folks, like people think of, they think of smart, they think of Einstein or some other mathematician.
Yeah.
Why is that?
But if you look at how Einstein thought about things, or like a great mathematician like Bill Thurston, or a great biologist like Dorothy Hodgkin, they would, they'd have abstract they would use the abstract symbols. They'd be very good at using the abstract symbols, but the representation of their work that they have in their head, you very, very consistently find that it's different to the stuff that they end up showing to people. So Einstein, there's this very famous quote where he was asked by a mathematician friend, how does he do what he does? How does he make his discoveries? And Einstein said, I don't think symbolically, I think mostly visually, or I have sensations of a kinesthetic or muscular kind that influence, I forget the exact quote, but the influence that he then turns into equations.
Wow, I never heard of that one before. That's pretty crazy.
Yeah, I mean, muscular, I don't know if there's my understanding is that is a good translation.
What's really fascinating is that all humans seem to sort of apprehend nature in terms of visualization. Like we sort of, what is it? Like something is brilliant, right? Or it's bright idea. Like these are terms that involve light and seeing. Like to have clarity or to... What's another one, Quinn?
Well, people talk about having a vision. Someone has a vision when they're a brilliant scientist. Or something.
Another one that I think is very interesting is how we can talk about concepts being close to one another, close or away from one another, even when they are tremendously abstract things. So you might say, I don't know, Kant's philosophy is closer to Heidegger's philosophy than it is to Aristotle's or something like that. That is all those three. Don't worry if you've never actually interacted with any of those things, but like that's the kind of thing that a philosopher might summarize as being true.
Because that's how people think.
It is how people think. You are born with certain abilities relating to space, certain abilities relating to interpreting visual information. 60% of the neurons that are coming into your brain are coming from your eyes. A lot of this information we sense visually, and the world of visualizations is very, very rich. There are a lot of complicated things going on in the world around in our everyday lives. If you think about something just like making a sandwich, it's a very, very mundane activity, but if you really examine it, it involves a huge amount of like doing technical things with your hands, and that's why a small child can't do it, and why it takes a lot of learning for them to do it. And building up those, it shouldn't be a surprise that building up these ways of interacting with the visual world, with the physical world, come in handy when we're talking about more abstract things.
Well, on an evolutionary scale, it's like humans went through the Stone Age, they went through the Metal Ages, now they're in the Information Age. And at each junction, it does seem like the ability to use tools became progressively more and more widespread, right? That's kind of what defines the passage of humans into the next era is...
Yeah. I mean, some people have even tried to define humans by their tool use, from what I understand.
Yeah, that's a pretty reasonable thing to do. Obviously, humans are not the only creatures that use tools, but it's certainly pretty fundamental to how we extend our abilities to do things. Something like the space shuttle, in some sense, that is a tool. This is very high level and abstract, of course, but thinking about what kind of tools we can have and what tools we can create right now that might be very generally useful, this is very important. I mean, something like Airbnb, it's a tool. It was created kind of recently. It wasn't created as soon as it could have been created. It took a couple of years. It took a little bit of serendipity for somebody noticing, do you know what, there's a need that people have here that can be fulfilled by us making this relatively simple thing. Yes, it's a whole lot of work, and a lot of people's careers dedicated to making this specific thing, focused on this specific task. But it's very, very important to emphasize that tools are something that blend into the background, something like a pencil or a desk, or a radiator. You don't notice them because you're just so used to them. But at some point, all of these things had to be invented, and that there are a bunch of engineers out there who make it their job and focus a lot of their lives on improving these tools, or making certain things to make it so that we can manufacture them a bit better.
So let's go back to tools for visualizing abstract information and concepts, because that's a really interesting tool that maybe hasn't been explored as much as, say, the hammer or the nail, or even the space shuttle. What's so difficult about these situations that makes them, or what's so difficult about these data sets that makes them difficult to imagine without visualization?
The first thing to say is that people aren't using visualizations that much, mostly because we've only quite recently had our ability to make visualizations hugely increased. So nowadays we all have computers that can do 3D rendering on them, and that wasn't really the case in the 80s. It was only the case in a limited way in the 90s. And physicists like Einstein and Dirac, again, even though they were using a lot of visualizations in their heads, they couldn't put them into their publications, or it was very difficult for them to put it into their publications, because printing is kind of complicated. There's a person that I admire a lot called Maria Gaetana Agnesi. I don't know how to pronounce her name perfectly, but back in the 1700s or so, she created the first good calculus textbook, essentially. And she actually had the printing press moved into her house so that she could monitor the creation of the figures, because she knew that the figures were the most important part of it.
Wow.
Isaac Newton was not so good with those. Sorry, the question was relating to visualizations.
I guess just how did you come to realize this was such an important gap that needed to be filled? Like, why do you, more plainly, why did you choose to spend your time working on these things? Obviously, we see how important visualization is to just existence in general for humans, but in terms of problems that need solved in science, maybe just tell us a little bit about your story coming to this.
I can answer the question very briefly first, which is visualizations are very beautiful, and visualizations are underexploited currently. Yeah, I'll give the longer story. So when I was a teenager, I was very into video games. Video games are it's possible to look down on them, but in the 90s, and still to a large extent today, video games are some of the most complex pieces of software in the world. Something like Call of Duty, I don't much like it, but it is an engineering marvel. It
demands respect. It demands respect.
Yes. Many millions of lines of code pushing our hardware to its very limit in order to make spectacular visualizations. Many layers of different kinds of visualizations, something like that you might take for granted, like smoke. Smoke is very hard to render. Glinting off a bullet or something like that is very hard to render. A tear coming down somebody's cheek, very, very hard to render. Skin is something that humans are very, very attuned to noticing little problems with, put it that way.
Hair too, right?
Oh, yes, absolutely. People dedicate their careers to rendering hair. Okay, so when I was a teenager, I was into video games. And video games, they're a mass market thing. They are visualizations. They're being sold to kids and teenagers and some adults, of course, but software developers do quite intricate things in order to entertain the users. They can have relatively complicated controls. If you look at something like Dwarf Fortress, it's got controls and it's got a simulation that's as complicated as anything you'll find in scientific software. Okay, maybe that's not quite true. But it's definitely getting there, I would say. And certainly it's more complicated than a lot of things that you can put in a good publication. Okay, so video games, really quite sophisticated. They shouldn't be underestimated. The games that I liked when I was a kid were stuff like Pokemon and Super Mario Land 2. I was hugely into that. When I was 18 or so, I played games like Portal and Braid and World of Goo. And these games they've got all of that. They are sophisticated simulations. And then there's a very interesting thing going on top of that. Even though Portal and World of Goo and Braid, these games are made to entertain, they explore quite sophisticated systems. So Portal, a lot of people have played, or at least they've seen it. It's a game about making topologically non-trivial three-dimensional spaces. So you have.
You sound like a mathematical physicist there for a second.
Yes. I've got to say it in the mathematical way. There's a simpler way of saying it.
So making shapes.
Or you make passages.
New shapes.
Well, you make passages, right? You make these portals and you use them to solve various challenges.
Yeah.
And so you have to have this very high level abstract ability to know that if you put the hole here and connect it to here, then you'll get what you want.
Indeed. or that if you put a hole here and a hole here, and then you do something with an energy pellet, but then you move this one over to here and that one to over there, then the energy pellet will move in a different angle and stuff like this. The game is about that, and the game explores that extremely well. It's really something that scientists, I would say, and science teachers should envy enormously. It takes this system that is, in some sense, extremely sophisticated. In some sense, it's quite simple because you can interact with it with simple controls. But it's taken a game designer to figure out how to make a bunch of simple controls to interact with this sophisticated visual system. You give that to the player, and then you design a bunch of puzzles to very carefully take the player through doing this relatively simple thing, and then this slightly more complicated thing. And then this thing, like there's a part in Portal where there's several parts where they lure the player into making certain mistakes, but they are mistakes that the player then notices, like, oh, wow, I just realized that I fell off this ledge, but I've realized that now I can go into this portal over here and that'll take me to where I want to go. And setting up this set of sophisticated things in the player's head that they then concatenate into solving really, really complicated puzzles. Portal 2, especially the co-op mode, has even more of that. And it's wonderfully fun. There is not a single point at which you don't feel like it's an entertainment product. It's something that is there to delight people.
So why did you decide to do science visualization instead of working on these really cool games?
Yeah, like, is there a direct line between the two?
There is. It was a slow line. I knew that I wanted to make game. So I made a game called Music of the Spheres.
Sounds like there's a monster in your apartment.
Oh dear, that would be a motorbike.
As long as it can't get in.
It's fine. So I made a game called Music of the Spheres. Music of the Spheres is about bouncing bullets. Inside of Music...
Whoa, you made a game?
Yeah. Music of the Spheres is a puzzle game. It's...
How do you make a game, though? You coded it and stuff?
I did, yes.
Gotcha.
I taught myself C++ while I was in doing my undergrad. There's nothing particularly mathematically or algorithmically sophisticated in Music of the Spheres, but I did take care to design it in an interesting way. And one thing that I noticed was that the game has relatively simple controls and a simple system where you shoot bullets and they bounce around. But I noticed that if you shot a bullet between two things and you made it ricochet back and forth, and then this thing starts slowly moving away, the bullet will be ricocheting like this, and then it'll be ricocheting, and the time between the bounces will increase slowly but surely.
Builds resonance. Yeah,
and I built a puzzle around that and set it up, and in some sense, it was built to be in analogy with the Doppler effect. There were other parts of the engine that were exploring things like trying to prove to the player that the square root of 2 is an irrational number. But the idea of the game was to contain little bits of science kind of emerging from the engine like that, or little bits of science, phenomena that exist in the real world, emerging from what's going on in the engine like that, and then to build puzzles around them, similar to Portal. And Music of the Spheres, not that many people played it. But
it's hard because you don't have a whole engine behind you to promote. And I mean, these video games, Portal, how many people worked on Portal, do you figure?
Oh, well, Portal is an interesting one. Actually, only 15 or so people worked on it.
Really? That's
Still
incredible.
15 people.
Yeah, that's true.
Yeah. Although the first version of it was made by Kim Swift. No. It was made by a group of about 3 or 4 students, a game called Narbacular Drop. led by this woman, Kim Swift, who's made lots of other very interesting games. Like Quantum Conundrum is another good example of a game like this made by her.
So you make this game, which is Music of the Spheres.
Mm-hmm.
But it seems like that game even is lending itself towards explanation as opposed to just entertainment. What took you down that road as opposed to just making Call of Duty 620?
Well, what's my personality type? My personality type is I'm kind of an academic kind of guy, and I like different ways of saying things to people, communicating things to people. And video games, in some sense, have still only just been invented. You know, they're only 40 years old, which is nothing in comparison with movies, music, painting. There's lots of really interesting things that can be done that nobody has done before. There's ways of communicating using interactivity that people just haven't tried, and they're trying lots of interesting things today. People like, you know, there's video games where you dance in certain ways, or video games where, like, I've just made another little video game where you watch a TV show and you play the game, but the TV show is like integrated into the game, stuff like this.
This is the prediction market game?
Yeah, Murder She Bet. But, you know, wanting to explore underexplored ground, that's a very worthwhile thing to go for. And I still feel, you know, it's been 10 years since I decided to go into the video games industry, though I left the video games industry in a strong sense. But I still feel like almost none of the territory that I thought would have been like, I would have thought that by now loads of people would have been make loads of really interesting sciencey games inspired by Portal. There's really only 2 good examples out there. No, maybe 3 good examples out there that I know of. There's one good game about anatomy called Incredipede. There's a good game about special relativity called Velocity Raptor. And there's a game about functional programming called Recursed. And most other games, they're not really trying the kind of Portal method for exploring interesting science. It's still really underexplored, and I wish more people would do it.
Why do you think that is?
Because...
why is science so unpopular?
At least in games, yeah.
Yeah, it's a good question. One thing is that, okay, a lot of the games industry is just people exploiting the Star Wars license or something like that. So you can kind of write all those people off. You can't necessarily expect them to make anything good.
I like Star Wars. I like Star Wars.
But not all of the sort of 200 odd Star Wars games that have been made are great games. Some of them are okay, but you know, Lego Star Wars is pretty good.
Sorry, I haven't played any of the games. I was just talking about the movies.
Yeah, they are very good movies. But yes, well, anyway, there's lots of things that you can do in games that are very, very lucrative, such as making people semi-addicted to playing a role-playing game where you kill monsters repeatedly, or making a game where you know, people raise carrots on a farm.
That's a game? Seems like they could be raising real carrots. That'd probably be better for everybody.
Oh, maybe. But you want something that you can get out of your pocket on the train. And to be fair, you know, people do need a way of escaping their lives, which might be quite difficult or quite dull at various times. And, you know, a video games industry providing things like that, there's nothing hugely wrong with it. But if you look at independent game developers, here's one reason why not many of them explore the Portal thing. A lot of them are obsessed with making stories in video games. And in my opinion, that is a project that is quite well explored territory. And, you know, sometimes it kind of works, but there are people who are so obsessed with trying to do slightly new things, even though they're not necessarily that new, with stories in video games. And all of the clever people try to do that, essentially. None of the clever people are so interested in combining science and Portal that they just don't bother. They've got other ways of trying to, they prefer this way of exploring what video games can do. And hey, maybe I'm wrong, maybe they will make great things one day, but anyway, that's a big part of it. Finally, people who are interested, one thing is that there are people making puzzle games that could try and do sciencey stuff. A large group of those people, as of sort of 2013 or so, they became kind of, I would say, macho male and tried to make more and more difficult games. And I've met people who they're very skilled at designing puzzles, but what they channel their abilities into is making more and more difficult puzzles. And making difficult puzzles is, interesting, and again, it provides people with entertainment that they would like. But again, I'd say that's what they're into, and they may be worried that if they try and do something sciencey, they'll come off as preachy or boring.
Well, that's a huge consideration, right? Because if you want people to be playing a game that has science in it, you almost have to make it so that the science is totally hidden. Like Portal, right? There's all this complicated stuff, but it's not centered on, you're going to learn about three-dimensional topologies and abstract thinking.
Well, I think there's an element about that where people are scared of these ideas because they're usually facing a test or, an exam of some sort. And it's like, there's like this innate, almost like Pavlovian, I have a really hard time with that one, Pavlovian response, where it's like these deep abstract problems are always framed in terms of a threat of failure, as opposed to a joy of success.
They've put people into fMRI machines and found that the mention of math problems or somebody explaining math to them activates the parts of their brain that are associated with physical pain. Partly because of, I would say, trauma from school, where you are, your ability with math in school kind of, it's in a sense high stakes, and it'll determine what your grades are or what college you'll go to, and it just freaks people out, and understandably, even if they were pretty good at it, they get a kind of imposter syndrome or whatever else, and they view it as really horrible, in spite of the fact that if they then walk into a beautiful place like the Alhambra in southern Spain, or they'll look at beautiful patterns of spirograph or MC Escher paintings or something like this, that'll obviously activate the parts of their brain associated with pleasure, because it's really nice looking at these things, even though they're totally mathematical. You've got to broaden your definition of maths a little bit to encompass things like that. But, I think about my mother, for example. She, hated maths in school, and a bit traumatized in experiences with her siblings and so on. But I look at what she doodles all the time, and they're these astonishingly mathematical doodles where she'll decide on a certain pattern that she wants to apply repeatedly, and
And so, what a cool teaching strategy to actually find somebody's interests like that and explain the mathematics behind it. I feel like there's this other element in addition to the intimidation where folks just think math is pointless. Like, they learn this stuff in Earth school and they're just like, I'm never going to use this. I got a calculator, or I just don't need math.
Well, there's also a question of intuition, right? So your mom doodles, but she's not thinking mathematically as she doodles. She just has a sense of symmetry and geometry and intuition of where to put a shape so that it makes sense with other shapes, right?
So it's like, hey, that's a cool symmetry. Here's what the symbol for that is, you know? We could symbolically represent it.
They're not thinking of it as maths, but can I read something to you?
Yeah, of course.
So this is so one of the greatest mathematicians of the last 100 years is a guy called Bill Thurston. One second.
What makes him great?
He proved something called the geometrization conjecture, which is something that generalizes to an arbitrary number of dimensions. So it's a geometrical thing that's true even if you're talking about 2 dimensions, 3 dimensions, but then also 4 dimensions, 100 dimensions, 1 trillion dimensions, infinity dimensions. And he discovered amazing things using his visual capacity. Nobody can visualize in 1 trillion dimensions. Nobody can visualize in infinity dimensions. However, Bill Thurston was extremely skilled at making visualizations that would give you in 2 dimensions and 3 dimensions that would then give you some insight into these things happening in more dimensions. And he proved that, for example, in 3 dimensions, you can break a surface up into triangles. So you can break a 2-dimensional thing up into triangles. In 3 dimensions, oh gosh, what is it? Well, there's certain things that don't generalize past 4 dimensions. Things like that work really well. Like you can break up any object into triangles if it's a 2-dimensional surface. But you can't do that in larger numbers of dimensions.
And ultimately, by dimension, you really just mean another piece of information here in terms of these matrix sets, right? Like if you're talking about tensors or something, you're just talking about slots of information that are bundled up. And these mathematicians have found a way to use geometry, which typically describes shapes, to extend it into the abstract space.
In 4 dimensions, you still have shapes. So
you have dynamic shapes, right? You're moving at that point.
That you're thinking about 4 dimensions as 1, 2, 3 spatial dimensions, and then time is the 4th dimension, right?
Yeah, well, I guess the only 3 that are spatial, or I guess the only ones that really pertain to shapes. Yeah.
Let me correct you on something. Actually, or at least from a mathematician's perspective, you can have there's time dimensions, yes, but you can have any number of spatial dimensions. So you can have 2 spatial dimensions and a triangle in 2 spatial dimension. Well, you can have a triangle and that's a two spatially dimensional thing. You can have a cube and that's a spatially 3-dimensional thing. 4 dimensions. Sometimes you will be talking about time as the 4th dimension. So physicists do that a lot. But if you were to talk to a 2-dimensional creature and the 2-dimensional creature said, oh, well, the 3rd dimension is just time, isn't it? You know, the 2-dimensional creature isn't familiar with the idea that you could have up, down, forwards, backwards, but also left and right.
Well, to be clear, there's no such thing as 2-dimensional creatures. Like everything in reality is actually 3. So everything else has to be an abstraction of some sort.
Well, tell me this.
It seems to me like these mathematicians have just found a way to use the concept of geometry to extend bundled information in a way that's honestly just more memorable. Like you can see the relationship this way as it's nested.
Is there any such a thing as a triangle? Let me ask you that.
If you draw it.
By definition, I guess.
Okay. Is there any such a... Isn't the drawing of a triangle kind of... It's got a little bit of thickness, so it's more like a triangular prism?
Well, the paper has thickness, right?
Yeah. But does the triangle have thickness? I mean, if you draw it with a pencil, then the pencil lead is, it's very thin, but it's a little layer, right?
Well, so you're talking about an abstract. We have to be really careful to not get confused objects and concepts. I mean,
that's absolutely right. So a triangle, you might say,
a concept.
Yeah. It's in our heads. It's not something that we'll really encounter. we'll encounter something like a cube if you've got like a sugar cube, right? But you don't really encounter a triangle. A triangle is just a two-dimensional thing, which is just a thing that we made up, right?
Mm.
But you can say the same thing about four-dimensional shapes as well. I can make up a triangle, a two-dimensional shape. I can make up a four-dimensional shape as well. And it'll be harder for me to think about because I have intuitions only about three spatial dimensions. I was born with a bunch of neurons in my head that are specifically adapted to helping me survive in this three-dimensional world. But as a mathematician, you can, for example, you can have a point that's a point in space described by three numbers, X, Y, Z, right? It's 3 along, it's 3 up, and then it's 2 forward, like that.
Mm-hmm.
So you've got a point, it's a three-dimensional thing, it's described by three numbers. You can also have a point described by two numbers. So it's just 3 along and 2 up, and it's just there. So what about if you had four numbers? Would that describe a point in 4 dimensions? Well, it's a strange thing to say, but if it's true that you can describe points in 2 dimensions, and 2 dimensions is just a made-up thing, well, we should be allowed to make up 4 dimensions as well.
Absolutely. You can make up as many as you want, like as many as are useful. That's what's cool about mathematics versus just regular physical reality.
And then what you find is that a lot of things from working with three-dimensional objects, for example, calculus that Newton did, these work in really similar ways up in 4 dimensions. And that can be pretty useful. For example, during my PhD, I made something called a Fitzhugh-Nagumo model. And that's a model of heart beating, essentially. It's cool. A model where, each cell is described by 4 numbers representing how excited it is. And those 4 numbers are related to one another with a series of little equations. And making a Fitzhugh-Nagumo model, you've got to think about these 4 numbers for each cell quite a lot. And sometimes you'll draw like a curve where it's like, okay, if this value is over here, then you trace up and this curve describes, where this other value will be. But again, it's 4 numbers, which means that if you were to have if you were to try to picture the relation of all of these 4 numbers as a shape, it would have to be a shape in 4-dimensional space. And 4-dimensional shapes are particularly useful for that kind of thing if you have 4 numbers describing a certain thing. And other shapes, okay, it gets pretty complicated if you're like a machine learning researcher and you might have a data set which has 100,000 dimensions.
But how do you even draw 4? How do you draw 4?
You can't draw it. What you can do is make drawings that are like...
It's almost like, sounds like it's sequential, right? You're like, if this looks like this, then it will correlate to here. And so it almost does seem like a dynamic representation, right? Because it's cause and effect that you're capturing in these 4 dimensions.
I can give you a simpler example then that isn't quite so cause and effecting.
Okay.
So you might have a sphere in 4 dimensions. Why would you care about a sphere in 4 dimensions? I can give you a reason. One reason is because quantum computing involves qubits, and the states, we say that for an ordinary computer, the space of possible values is 0 and 1. So it's kind of like if you wanted a way of picturing 0 and 1, you might just say they're points on either end of like a line. You're either here or you're here. You can go from here to here. If you wanted to have an equivalent picture for a qubit, you need a 4-dimensional sphere, it turns out. And
why do you call it a sphere, though, if it has 4 dimensions? Is it like, why do you even use the word shape, honestly? Like, if you can't actually represent it on a piece of paper, or like, if you can't actually visualize the thing. Yeah. Why is it a shape?
So if you write out the equation for a circle in 2 dimensions, probably a lot of people will have encountered this in school. Here's the circle, and we want the relation of this number, how far, if you've got a point on the circle, you want to know if the point is this far along on the x-axis, what's its y-coordinate going to be?
So you can define them with abstract symbols like mathematics, but you can't actually represent it visually. Like the shape of the circle is defined by its outside and its inside. The boundary defines the circle, right? Like as a drawing, as a physical object, like if we had a wheel, we'd be like, its shape is defined by its surfaces, its boundaries. Yeah. But when you go into these higher dimensions, you're not really talking about shapes anymore.
What's your objection to calling it a shape? I guess let's start there. This is I don't want to call it an axe to grind, but Mickey has a lot of opinions about 4 dimensions.
Oh, great.
Well, I got opinions about everything.
So we've wandered into territory that's very touchy subject.
Sure,
and I think that the issue at heart here is the fact that when you start talking about 4-dimensional or 100,000 dimensional shapes, it becomes exactly, you put it in quotes.
Shape quotes, yeah.
And that's a tricky thing, because for someone who doesn't necessarily have a good sense of abstract understanding of the mathematics, they're like, well, what does it mean that it's a 100,000 dimensional shape? And it sounds like even with you didn't finish your example of the 4-dimensional sphere. So let's go through that, and then we can kind of trace back.
I can give. Well, okay. No, I've got a better way of doing it.
Okay, let's do it.
3-dimensional objects cast shadows, right?
Yes. Well, it's not an object, but it is a shape. Right? There's a distinction between object and shape here.
Yeah. So, words are difficult, right? I'm kind of glad that, I studied philosophy, and it kind of helps me out in sort of metaphysical situations like this. Put it this way. Suppose that we had a word that people were very passionate about, like freedom, right? In the United States, definitions of freedom and whether it counts as being deprived of freedom if somebody makes it illegal for you to own a gun, that's a really, really important thing. And for a lot of people, that debate comes down to the definition of freedom, right? Really important word. But this person says that freedom is X, and this person says freedom is Y, and apparently both sides would say that people's lives kind of depend on how we're going to define this, or maybe the word rights.
I think you had a really good point there. I think shadows do have a shape, actually, but I'm not sure the 4th-dimensional things do.
Well, put it this way. Shape is a thing that we got used to as we heard it when we were young. We were taught that's a shape and that's a shape.
Do you have a definition? Wait. Do you have a definition for shape?
No,
I just threw one out there that works, though. I think it works for what you said. Like, if we have a boundary that separates the inside from the out,
it's an object, though.
No, it has a shape. A volume that has the boundary that separates the inside from the out is an object. But as far as the triangle, it has like a demarcation from the inside from the out.
Yeah.
But I'm not so sure these 4, 5, 6-dimensional things have those demarcations. But
there's an interesting shape called a Klein bottle, which is technically 3-dimensional, arguably 4-dimensional, but it's characterized by the fact that it doesn't have an inside or an outside.
Like a Mobius strip or something.
Oh, it's you can make a Klein bottle by taking 2 Mobius strips and gluing their edges together.
That's
so
it.
So shape is not a word that mathematicians use in a formal context.
They only abuse it, actually.
You're right. You're right.
Don't take me too seriously, man. I'm just having a.
But there are some. There are some things that a mathematician will say, "Oh, this is a shape," and I will say, "No, come on, that isn't a shape." Or they'll use the word shape in a very vague way. Note that you could say the shape of Joe Biden's political beliefs. That's a figure of speech that people use sometimes. Again, we're going back to like using.
That's like a metaphor, though.
Yeah, exactly. It is
so maybe these fourth, fifth dimensional things are metaphors.
That's a fairly reasonable thing to say.
Whoa.
It's philosophical. I mean, people debate whether these things actually exist, right? I mean, in a manner of speaking, again, I made a Fitzhugh-Nagumo model, which I haven't practically used it. I just wanted to visualize the Fitzhugh-Nagumo model. But some people have actually saved lives using the Fitzhugh-Nagumo model, right? So the Fitzhugh-Nagumo model is very, very useful. It's a thing that exists in 4 dimensions. But it's turned out to be really, really useful for certain things that scientists do. Does that mean that the 4-dimensional shape that the Fitzhugh-Nagumo model, the 4-dimensional shape that the Fitzhugh-Nagumo model describes exists? It's a 4-dimensional thing. You can't picture it. You certainly can't. You'll never like bump into one in the street.
Hold on. Does it exist or does it occur?
Yeah, it's just a model, right? It's an abstraction. Like, we like to just think that concepts don't really exist. They just occur. It's like an idea. But objects, that have actual volumes with borders separating the inside from the out, those exist. They have a location somewhere. And so
I might point out to you that, like, okay, let's say that I've got a box. So that meets your definition. It separates the inside and the outside. No,
as long as it has to be somewhere too. Like, it needs a definite location.
Okay, fine. That really exists. But I mean, if you were to look at a sugar cube or any other object that you like made of atoms, you just look at it really close up. What shape are the atoms? Well, an atom is mostly empty space, actually.
The trick is you use the word look, right? You were like, look at an atom, but clearly atoms are smaller than the wavelength of light. And then it's like, well, we could touch them with an AFM, or it's really weird, right?
But the question is, does the shape of a sugar cube distinguish the outside from the inside of the sugar cube? This is all tremendously philosophical, of course. Let me bring it back to so visualizing an atom is another example of something that's really quite abstract. I mean, the thing that you encounter in school is like a bunch of little polystyrene balls that are colored in, and you've got another ball that's going around it. If you grow up and study chemistry or physics, then you'll be like, okay, it's more like there's sort of a cloud around around another different kind of cloud in the center. And then you kind of measure little bits of the cloud one at a time. And from that, you get an idea of what it's doing when you're not measuring it or something like that. Visualization.
We're about to launch a channel called Demystifying Atomics, where we visualize the atom without clouds or any of that stuff. Plug in that real quick.
No, really? Okay. Well, I was just going to say that the clouds, rendering the clouds is a nice way of visualizing the atoms.
Well, because that's what acts as the surface of the atom, right? Like, if you look at chemistry, there's a surface of the atom that's interacting with the surface of another atom.
The electron shell.
The electron shell, exactly. And so that is a surface that would lend the atom in the characteristic of an object that has location. The sugar cube is obviously a composite object, right? That's made up out of atoms, and so has this sort of, I don't want to call it a meta shape, but I'm going to call it a meta shape, right? Because you have...
It's just a shape. It's just
well, it is a shape. Well, it's a shape. It's a composite object. It's a composite shape. It's the atoms... Because, I mean, honestly, the sugar cube is different from a molecule of a sugar crystal, right? The sugar cube is made out of many sugar crystals that are combined into an object. So you have all of these different scales at which you still have objects.
Yeah.
And so, you can zoom into the sugar cube and you can look at the surface and you can be like, well, the surface is not necessarily the true surface because there's some kind of exchange. There's, it starts to get fuzzier and fuzzier, but at the end, they're still objects and they still have location. And
yeah, it's almost really interesting that the humans refer to the atom's surface as cloudy. It's almost like they're like, we haven't resolved this yet.
Yeah. To be clear, mathematicians... So asking questions like this has led mathematicians to very interesting places, I will say. So some of it's kind of philosophy-like, but some of it, again, is quite practically useful. So one of the more important things of the 19th century was a mathematician called Riemann inventing something called a manifold. A manifold is the closest thing that we have to a definition of shape. In math, yeah. So the word shape is, again, a mathematician might use it in a lecture, but they'll say, oh, but that's a rather informal word. I'm not trying to do proper math when I say shape. I'm just trying to give you a vague idea of what's going on here.
And topology is the proper word?
Manifold.
Proper? Manifold, sorry.
It's quite close to being the proper word, but there are manifolds that you might be like, that's not very much like a shape. And then there are shapes where you're like, yeah, that's definitely a shape.
So they're like metaphorical shapes. They're like abstracted versions.
They are one of the best definitions that we've got. The definition goes like this. If you've got a manifold, you can look at any part of the manifold, and if you look really, really closely at it, you can go in different directions on the surface of the manifold. For example, if the manifold might just be a single line that's like wiggling through space, you can look really close up at any part of the line, and so long as you can go this way and that way a little bit, then it's definitely a manifold. Yeah. And
in this sense, you mean metaphorical motion because you're moving between different matrices, I imagine. Moving, quote unquote.
Yeah, it is indeed moving, quote unquote.
There's a solution for the next point, basically.
Yeah, pretty much.
So you can graphically represent it, where if you can move along it, which means that it's a continuous...
You've quickly gone to a place where I have to say no. No, you can't graphically represent it because here's one that's very practically important. So the space that we exist in right now is a manifold. It's a three-dimensional manifold. We know from Einstein that it is curved in places. So if you look at photographs of space taken near black holes, you'll see that some of the shapes are cut, some of the stars are kind of like bendy because some of the light from the star has gone close to a black hole and bent around it.
Well, it refracts it, right?
Impression of what it looks like.
It refracts the light.
I think the humans think there's something else going on.
Refraction is a slightly different thing where the light goes into something and then it comes out at a different angle. In the case of a black hole, it's literally the case that I don't have any pieces of paper around here, otherwise I'd use a piece of paper, but it's literally the case that instead of the three-dimensional space around the black hole being just flat in every direction, it's curved in the same way that a rubber surface might be curved. So the shape of the manifold that is our universe nearby that black hole has gone from being flat to being curved because of the black hole. And as a result of that, the light, which ordinarily goes in a straight line if it's going through something flat, but it's gone through this curved space, and that's resulted in it hitting our telescope in a slightly strange way, resulting in this bent, curved image.
Well, I think what really, really confuses folks is that what Einstein really meant by space and time are different measurements. And so the entire theory really just describes how things behave, right? It's describing how different bodies behave in the presence of other bodies. And so you really have this extremely descriptive scenario that's called a theory, but it really doesn't have a mechanism. It's not like telling you why those things move. Like saying that the space is curved is really just saying that objects move in a funny way around each other.
Let me disagree with you again then. Note that Einstein was the example that I used at the beginning of a person who thought about shapes, and he thought about things bending and curving in response to forces. Again, he was actually thinking about, so his muscles. It was through thinking about these sensations that he developed this theory. And then at the end of the day, you get this bunch of equations, and some people, you can be perfectly productive with the attitude that this bunch of equations is just something that I'm going to use. I shouldn't try to picture it as a bunch of shapes. It's just something that'll tell me what result I'll get if I use a stopwatch, and I do this and I do this, and then I'll get the number out of the stopwatch, or I'll put a ruler here, or I'll measure, this light ray coming here and this light ray coming here, and it's just something that tells me the numbers.
Well, Newton was kind of more like that, right? Well, like Newton, your famous Brit, Newton. He was way into this is how the planets move according to this inverse square relationship, but I'm not going to even try to explain why they do it or how they do it or what the mechanism is. That's totally beyond me. And the weird thing with Einstein is he kind of refined Newton's description of the way bodies move, but there's still no mechanism is the thing.
Yeah. That's a different question, I suppose. Yeah. So I suppose with what I was just saying, I wasn't talking about the mechanism. I was just arguing that Einstein was thinking about shapes.
Quote shapes.
Right. So I guess that the place where I think that this is all centered on is the relationship of 4 dimensions and onward to objects. Right?
Yeah. To the real world.
To the real world. Exactly. And so what we've come to is that mathematicians will casually refer to things that have more than 3 dimension as having shape. Yeah. You suggest that the more accurate term for that is manifold.
Yeah.
And that, but we still haven't gotten to the point of whether or not something that is in 4 dimensions or 10,000 dimensions. You say that the manifold is not something that can be graphed. In terms of physics, hold on 1 second. In terms of physics, the 4 dimensions, like we started out with, there's 3 spatial dimensions and the 4th is time.
Yeah, sure.
Right? So that means that 4 dimensions is basically the ability to consider things in a dynamic frame.
So, I'm afraid no. Let me backpedal on that again.
Okay.
So put it this way. Suppose that you are drawing a graph of the US's employment rate against time. Pretty important graph, right? That you would see day to day, see it in a newspaper. Okay, on that graph, time is this dimension. And what's this dimension? I think
Quinn was just talking about physics again, just wrapping up the Einstein discussion.
Oh, sure. But the important thing is that there's a definition of 4th dimension that has nothing to do with time.
It's just a mathematical index, right? It's like this is the 4th relationship we're talking about here.
Yeah, but once again, you can consider a 4-dimensional space as a 4-dimensional space with shapes in it.
I see, because space doesn't mean the distance between objects in mathematics. It just means the whole set.
A set of numbers?
Set of whatever. Set of abstractions.
We've got this term in mathematics, which is Euclidean space. And that means the most ordinary kind of space that you can imagine. That's flat space. So a straight line or a flat sheet.
But the space word means just your set of information that the graph is talking about, right?
Mm-hmm. I mean, a set can... the way, I mean, some sets you picture like as a bunch of like just points that are not necessarily, I picture a set as like a bag, like I've got a sack on my hat, on my back, and the set contains like sandwiches, or it contains negative numbers, or it contains fractions or whatever. So that's the way I would picture a set. The way that a mathematician algebraically writes a set is with curly brackets.
I guess I didn't really mean the set, like in the math. It's a hard word.
Right?
Like mathematicians have taken all these. I guess I just mean like the whole shebang, right? It's like space just means everything here, like all of the different abstractions that we're talking about. All the dimensions. Like it is the landscape on which this discussion, this mathematical description, is going to take place.
Yeah, that's very, very general. That's very general. But I do. But words like manifold, or words like again the Fitzhugh-Nagumo model, this set of 4 numbers with certain relationships between each other. These define pretty well understood mathematical things. Yeah, and well, that's the kind of thing that I would. That's the kind of thing that I picture whenever I'm talking about like 4-dimensional this or that.
Got it.
Yeah.
And so abstract mathematics has been really useful for engineers on Earth, from what I understand.
Yes. Very, very useful indeed.
And I mean, that's the beauty of developing tools that allow you to interact with these abstract ideas. Because I think that what all of this has centered around so far is that we'll often come at these questions of mathematics from a physical perspective, right? Because there is the world that people live in, which is very much not abstract. It is the physical objects that you touch, the things that affect you. Then you have the conceptual world, which for a lot of people is bordered by the things that they experience mentally, right? Emotional states, memories, things that happen on the inside, ideas that you have, relationships. Yeah. So that's kind of the lived experience. And then beyond that is the world of mathematics and the world of
symbolic representation, quantitative symbolic
representation about ideas that are very, very complicated, right? They get really complicated really fast. You go into a 4-dimensional model of the model of the heart cells, and all of a sudden you're at a point where you can't draw this. There's no object that you point to. It's all of these things happening at once or sequentially, but they're happening together. They're interdependent. And the only way that you can write them down and talk about them with somebody else without sitting there and basically writing a book about what exactly is happening is that you have to deal with equations. You have to deal with mathematics. You have to deal with something that is far, far outside the lived experience of most people, right?
So yes and no, simply because just remember that a graph works really, really well in some situations. Sometimes I wish that journalists would use more graphs. For example,
freak people out real bad.
They do. They can freak people out.
However, it's
tremendously useful. And anybody can look at a graph that's doing this, boosh, like that, and be like, okay, something happened here. Right? Anybody can look at that. And that's a fairly intuitive thing to be thinking about. That's why, a movie can have like a heart monitor as a rather abstract thing. The thing to say is that sometimes you can have something that's represented by an equation and the same exact thing represented by a picture on a graph. And sometimes this one is useful, and sometimes this one is useful. The place where I'm at is that we don't use this nearly enough. There's so many ways in which we could use this that we currently aren't using.
And that's hard to argue with, right? Like that's just a basic understanding of the world where the people who are really good at math will use equations to talk to each other because everyone has their own system of visualization. Presumably, there's nobody in the mathematical world who, when they hear an equation, just still thinks about the numbers rather than some relationship.
No, there are some people like that.
Really?
Oh, yes. In fact, it's quite controversial. It's as controversial. It's one of the most controversial things in mathematics. Yes, there are some people like that. I mean, Einstein, I've not heard anybody other than Einstein talking about the muscle thing, by the way. Most mathematicians are using some amount of visualization, but here's an important story. There was a group of mathematicians called Bourbaki in France in the 30s, I think, or that's when they started. It's quite a long history. And they were some pretty hardcore mathematicians who discovered some pretty impressive things, as I understand it. I'm not in that field. But they specifically said, visualizations are awful. We must stop using visualizations. Death to Euclid, death to triangles.
Whoa. I'm fighting words.
Yeah, the story is that a member of the Bourbaki group was thumping on the desk during a lecture, and there was let me give you the other example. So an important mathematician from about 300 years, okay, I don't know when he was, but long before this, guy called Louis Lagrange. Maybe French people do this more than other people. So he wanted to go in the opposite direction from Maria of Agnesi. He wrote a book about Newtonian mechanics that's really important. He invented something called the Lagrangian, which is very important for engineers and very important for lots of physicists. His book was completely algebra. He wanted to step away from having pictures and defining things with curves, and use just the algebra, because the algebra, the idea is, Lagrange and Bourbaki said, if you do this, you're less likely to make mistakes, because mistakes come from informal thinking about things.
Well, it makes sense that they're going to try to advocate for their art. I mean, they've developed a really rigorous set of sort of consistent derivational logic. It's like, why wouldn't they think that's the best way to represent nature?
Yeah, I mean, it's a whole big thing. I mean, the unfortunate thing might be fundamentally to go around saying that this is the one way of doing it. Viva la différence sort of thing. Just say, hey, do you know what? Sometimes use this, sometimes use this. Don't think of it as like, oh, here's the one tool, and once I give everybody this tool, they'll be able to solve every problem. No, it's more like you're going to go through your life and you're going to face various problems. If you're doing a PhD in maths, or you're doing a PhD in biology, or you're doing neither of those things, but you're trying to figure out like what's the best mortgage to go for, or something like this. You want to use this tool or that tool, and you want to use the best tool for the job. And you never stop learning new tools, even when you're 50 years old. There's always a tool out there that could make your life a little bit better.
Do you face pushback from other mathematicians when you start talking about developing visual tools?
Yes, I do. What's the worst I've ever had? I mean, my professor, I had a professor who very much influenced me, and he once got told off he was a computer scientist, and he got told off by a very famous other computer scientist called Dijkstra for trying to use visualizations in a lecture. Dijkstra said, no, stop this. You're a load of rubbish. You want to be keeping to this algebraic way of doing things so that you don't make mistakes. And that probably, lessened his reputation. I don't know if it ruined his career, but I don't know. I think he didn't hang around with Dijkstra. Dijkstra didn't want to hang around with him that much after that. But a story about me, so some of my friends laugh at me in an affectionate way. They say, "Oh, come on, Hamish! Like you're bending over backwards to do this thing visually, but you might be just better off doing it in this more algebraic way." That's
well, you can kind of see where they're coming from because you inherently have to lose information to step down dimensionally, right?
Oh, that's absolutely true. Yeah.
But that might be just what someone needs for the light to go off, so to speak.
On?
On. Light goes on. Sorry.
Darkness is usually the antithesis of what we're looking for in learning.
Again, more visual metaphor.
Yeah.
I mean, one thing to say, okay, the best argument against visualization is that it's quite a lot of work. Sometimes, for example, okay, I've spent 2 years, no, a year and a half now, trying to visualize geometric algebra in a certain way. That's my current project. That's a lot of work. It's work I could have spent doing something else. But again, we just haven't explored this territory very well. And by exploring it in the right way, I think we'll find ways of making it easier as well. There's lots of people working on visual programming languages, for example. And once you have more of those, you can have more visually oriented people engaging with programming or engaging with
like hieroglyphics or something?
No. The usual way of doing visual programming is that every function becomes a little box. Beg your pardon. Functions and objects become boxes. Like, oh, this box is going to be this number. This little box in here is like my age. And you have a little arrow coming out of this box, and here's like a function that's going to like figure out how long it is until my birthday, because it's got like this other box.
I see what you mean, like schematic, almost like electric engineering diagrams or something.
Oh, yeah, very much so.
Is this how programs like LabVIEW work?
But also games industry stuff as well. So there's many companies. I was quite annoyed actually to find that the Unreal Engine really is a tool for designing games or making games, and it really insists that you use visual programming. And I actually don't like the kind of visual programming that Unreal Engine uses. I would prefer to be using a text editor. So that's one sense in which, maybe people, for my tastes, people have bought into this way of doing things a little bit too much.
Why don't you like it?
Because it involves making lots of decisions about like physically moving stuff around. It also gets very, very messy when you have 200 variables or something like this.
I've heard it can be really difficult to follow somebody else's work.
Oh, yeah. I mean, to be fair, that's true in normal programming as well. True. And I'm working completely on my own, so I don't get to make that excuse.
Well, past Hamish and present Hamish are maybe not the same people,
Oh, that's a good point. That's
interdimensional Hamish.
Interdimensional Hamish.
Yes, Hamish extruded a long time. But yeah, it's a good question. I heard of a philosopher once who doesn't have a pension plan because he's committed to the idea that his future self is not the same, is a different individual from his current self.
Let us know how that works.
Wouldn't you want to help? Well, that's a different rabbit hole.
It's a philosophical thing. But anyway, another reason is that the mouse. I don't necessarily like using the mouse that much. I prefer to be doing things with just buttons. And a mouse is a wonderful thing, and it's a very visual way of interacting with lots of things. However, you shouldn't have to use it's not so good if you have to use a mouse to go through loads and loads of menus. It would be better, if possible, to just press a button and there's the menu that you want. And so some people get RSI from using the mouse too much. So I want to avoid that kind of thing. And so where possible, I try to make it so that I'm doing things just by button interaction.
And this This kind of brings back the idea that visualization is not always the gold standard. Right?
Yes.
Because I mean, so on some level, programming by writing things out the old-fashioned way, at least in some cases, makes more sense than doing it through these visual blocks. Because it's what you said originally, which is that your friends were like, "Come on, man! Like this is more complicated than it needs to be." Because just force yourself to think about it in the abstract.
But it might bring somebody into the art that wasn't interested otherwise.
Yeah, exactly.
But how about this? I mean, possibly we just haven't yet invented the right visual way of looking at it.
Sure.
So let's boil it down to the simple choice confronting me, which is I can use this bunch of boxes and wires, or I can use ordinary looking code. Now, this is the way that I prefer doing things, but it should be admitted that this does have a load of drawbacks, even in comparison with this. For example, it's not so easy to see in here that this variable is directly impacted by this variable. Whereas in here, you can see, if you wanted to answer that question, if I had it laid out this way, you could answer that question in a couple of seconds. Over here, it might take more like a couple of minutes. And that might be really annoying if you're a person who's sitting down to use it, to look at this for the first time.
So again, it's all about diversity of perspective.
Yes, or there might be some wonderful middle ground that we just haven't found yet. Another way of doing it, fairly soon we might have computers directly wired to our brains. And that'll make it so that you're not using the mouse quite so much. But that'll also make it so that we can create visualizations very, very quickly. And navigate things very, very quickly as well, instead of having to pan around them as we do, or use loads of scroll bars, or change tabs, change windows, this kind of thing.
Is there an intermediate step to that where programming can just be in normal written language? Like, why can't you just go to a computer and be like, okay, computer, use whatever language you know best suits this task, make me a program that can take this input and do this to it?
Lots of people have tried that over the decades, and one of the most impressive things is from recent years. It's GPT-3, which is a artificial intelligence where you can describe in ordinary language a web page, and it'll do its best to make that web page. Wow. This approach suffers from problems, and it's a problem that's highlighted by the discussion that we had earlier. Suppose that somebody were to use the word shape in the context of describing something to a computer. What exactly does shape mean? Well,
it's multivalent.
Yes, sure.
These multivalencies are...
You mean like multiple definitions?
Yeah.
Yeah, exactly. Yeah, it's an ambiguous term.
Well, lots of words mean multiple things.
Depending on the context that you're using it in. We kind of settled on the fact that physics shape and math shape are very different things.
Physical.
Yeah, it's true. The problem that you'll have is that there might be loads of things like that that are fairly hard to describe to the computer, and are even not necessarily known to the person who's spoken the words. I mean, suppose that you hear some people say sentences that don't make very much sense sometimes, right?
And yet the people can understand
I'm one of them.
Yes. Some people can understand them, or some people feel like they understand them. Sometimes people kind of nod and smile, and even if somebody's just said something that they don't understand,
the pity smile. The pity smile.
Or it might not necessarily be a pity smile. I mean, suppose that it's your teacher saying something, and it's something that is going to be really important to you, and you're going to need to understand at some point. But maybe you'll think to yourself,
smile.
Embarrassed smile, or faking it, just faking it.
Straight faking up fakery.
Yeah, until, a couple of minutes later, they'll go, Oh, I see. This is what you meant by that thing that you said earlier.
Fake it till you make it.
Yeah. Humans do that all the time. Really a lot. And it's a big part of being human, dealing with that ambiguity. I mean, for example, humans have implicit stuff all the time. Flirting, for example, you might reinterpret, you might, think back to something several hours ago and go like, oh, that person was maybe flirting with me or something like that. That was like, and but it took a huge amount of reflection on the context of the words that they said in order for you to get there. Language is designed for this. In fact, that's one of the main things that it does, I would say. And so when you have a world full of people kind of going like, oh, I'm going to say this and you're going to follow my instructions. And then they say a bunch of things and the thing kind of does what they want, but they're like, no, this isn't what I meant. But like, actually the person who followed their instructions, they were actually making a pretty darn good interpretation of what that person said. It's just that this person has changed their mind about what they said earlier. Again, that happens all the time. And
does this sort of ambiguity happen in quantitative languages like mathematics too? Like, is it possible to have a symbol mean more than one thing depending on the context?
That would be terrifying.
It would be terrifying. And then you're certainly supposed to avoid that in computer science. The idea is that you try to create, big standards such that if I'm writing a compiler for C++ and you're writing a compiler for C++, they should, and somebody gives up both of our compilers some C++ code, both of them will do exactly the same thing. However, something like, for example, the OpenGL standard, which is very important for visualization, there are ambiguities in the OpenGL standard, and different chip manufacturers can interpret them in different ways. And it doesn't necessarily make that much of a difference. It just changes the color of this slightly red color to this slightly less red color. But you can certainly, well, I can't think of a good example, but that's an example of an ambiguity for a programming tool.
But it's rare that it would say red in one language and be or not even yellow, but just not even a color parameter in another language.
Yeah, I mean, this is a very deep problem. Well, in some sense, it's a very simple practical problem. If you think something, if you and I disagree about the definition of
shape,
programming, shape, we can try and get together, and if it really matters to us what the definition of this word is, with a lot of work, we might be like, okay, tell you what, let's have two new words, and this can be this definition of the word, and that can be that definition of the word. Totally. That's the kind of thing that an engineer might do, that a philosopher and
or a scientist.
Or a scientist, yeah. Philosophers try to do that a lot. As in a word like freedom or a word like free will or morality. For a lot of philosophers, their sort of philosophical technique is to say, okay, let's just try to split this relatively ambiguous word up into the various definitions that it can have, or the various different contexts in which it gets used, and then maybe we'll find a formal definition of it that way. Same with a lawyer, right? A lawyer has to interpret words and come to decisions about what these words were meant or supposed to mean. That a lot of people are kind of, getting interested in using computers to implement certain laws, and AI gets involved in that as well. The thing is, though, what we've discovered from the last 10 years is that artificial intelligence comes in very handy, more and more. Artificial intelligence, though, is generally based on a very, very large pile of human intuitions. Deciding whether a picture contains a set of traffic lights or something like that. It's got loads of data of pictures and people saying, yes, it's got traffic lights, or no, it doesn't have traffic lights. And then you can get an algorithm out of that. But the algorithm will fail in, for example, I saw a wonderful video the other day of somebody's car, and the car falsely believed that there were a bunch of traffic lights in front of the car. And the reason that it falsely believed that was because there was a truck in front of the car which was transporting a bunch of traffic lights.
Wow.
Right? Or it thought, another classic one is that the car thinks that there's a bicycle going across the road, but actually it's just a bicycle that's attached to the back of a car or a truck. Fairly common situation to be in. And what we find is that artificial intelligence, to the extent that it's working right now, it's kind of filling in gaps in, sometimes dubious ways, and showing us how much implicit stuff there is when we communicate. I mean, I say the word shape to you, and you think you know what I mean by that. In general, it'll be hidden that we might have disagreements about the definition of the word shape.
Right. The conversation has to go to a certain depth before the disagreement or the ambiguity even begins to emerge, because you can have a conversation where two people are like, I totally get what's happening. Yeah. But they're actually having two parallel conversations where the real disagreement only emerges when one person says something and the other person's like, wait.
Yes. But let's not act like this is a bad thing, because people having different perspectives is how people are able, being flexible about the definitions of words, that can allow people to come out with new ideas or new arguments for a certain point of view, for example, which is the kind of thing that a computer can struggle with. Yeah,
definitely. So to kind of, we've been talking for a while, and I want to wrap it up a little bit.
Sure.
What is your vision of the future look like? You've been making tools, you've been making games, you've been finding ways to visualize complex, abstract ideas.
Yeah. My vision of the future is, first of all, not everybody likes this part of my vision of the future, but it's an inevitability, and it opens up a lot of interesting things. So in 7 years' time, we're all going to be walking around with spectacles that allow us to have computer visualizations anywhere we like at all times.
Wow. Yes. You think it's inevitable?
Inevitable. It's a natural progression after smartphones. A smartphone is something you've got to hold with this hand. Whereas if you have these spectacles on, you can snap your fingers and now there's a screen floating here, right? That's a little bit more useful than a smartphone. The only things that the things that we have to struggle with right now are stuff like the fact that these spectacles don't work very well in direct sunlight. And that's unfortunate. It might mean that for the first couple of years of them being used, people only use them indoors. And so people spend more time indoors, and that's a pretty bad thing. I don't like that. But if I'm allowed to go even further than that, looking 20 years into the future, for example, okay, we have computer visualizations around us whenever we like, and we can get rid of them whenever we like, hopefully. We're not surrounded by adverts. I'd very much dislike it. But the visualizations that you want, for example, you're in the shop and you want to know whether this toilet roll or that toilet roll is a bit better for the environment. Right now, all you can kind of do is like, oh, here's a logo from this company saying that we did pretty well. Or, but, you want to be able to get up information. You don't want to be standing there in the shop for too long, but you want to have information on anything that you want. I mean, if you're walking down some road where some really important historical thing happened that you don't know about it because it's just a road that you're walking down, you'd kind of like that. And it should be cheap to set that kind of thing up. right now, okay, you got like a plaque maybe, but you'll only have that if somebody's stumped up the money for it, and in order to maintain it and that kind of thing.
And if the building hasn't been torn down that the plaque is on in the first place.
All right. If I'm talking to you about some political hot topic, I want to have visualizations involved in that.
Mm-hmm.
If either of us says some spurious thing, like 30% of people like this or whatever, if there's information available that's pertinent to that thing that we've just said, I want to see that information right there. I want to see a graph from the scientific paper, ideally the meta-analysis, that shows the thing that you just said, or shows that the thing that I just said is false, right?
Do you think that'll cut down on arguments or increase arguments?
I don't know. I don't know. But I know that I want it.
I feel like then it boils down to like, well, who paid for this study?
Oh, well, that it can boil down to that now. And, if people are going to say that, then it's like, well, why bother using any information whatsoever? If you're going to tell me that 20% of Americans believe that, the Earth is flat or something, like, no, not
well, 20%. My God, someone needs to look into that.
Sorry, I was thinking about no, that's not true. That was totally just the thing that I was thinking about was that it's something like it's between 20% and 40% of Americans believe that the Earth is less than 10,000 years old.
Oh, I'll believe that. The flat.
But it's dubious. Okay, quite right. You've got to be looking at sources, and I want that information as well. I want it to be saying, here's the source of this graph that we're showing you, right?
The future will require more access to information, but also more information about the quality of that data.
Well, there's this thing I wanted to interject that Quinn and I talk about all the time, which is like deep fakes, especially visual stuff, right? There was a point in time where photographic evidence was damning, right? But one can easily imagine a place in the future where, a photograph is not reliable testimony that something even happened on Earth. How is that going to change the news? And maybe people will actually have to do information in a totally different way.
My understanding is that deep fakes are relatively easy to detect, not for a human, but there are algorithms that people have developed that, and it might become an arms race, right?
So like you could get an app on your screen to tell you when something's not real?
Yeah. I saw something on Facebook actually the other day, some video that somebody had sent me, and Facebook had a little drop down saying this contains, I forget what their wording was, but misleading information. And I was like, oh, that's kind of interesting. Maybe obviously it's Facebook saying it, anyway, deep fakes, that's something that I don't have any expertise in, I'd say.
Well, I think that this kind of just comes down to the idea that when you're suffused with more and more information, it becomes more and more difficult to assess the quality and the veracity of that information. And so with an I love the vision of, I love the vision of the future of there always being information available to verify, not even verify, but cross-check the information that people put down in conversation. People do this right now anyway. Yeah, exactly. Where did this idea come from? Who's been talking about it? Is it robust? That's a beautiful idea, especially because so often people have technical conversations and they need that. And they do it on their phones anyways. And instead of having it right at their disposal, they have to go Google or DuckDuckGo or whatever it is that you're using.
It's often considered a bit rude to whip out your phone to look up something in the course of a conversation. And, I can see why people have that perspective. I would say that we should normalize it, though.
Agreed.
Yeah. another aspect of the future, though. It's not just, visualization is useful for other things other than, I don't know, giving a smackdown to somebody.
That's my preferred use of it, though.
What could be more fun?
Yeah, exactly.
So I think that for kids learning stuff, they should be able to learn extremely technical things, the likes of which we would consider to be like postgraduate stuff right now. A field like vector calculus or linear algebra, quantum computing, computer graphics, all of these things should be incredibly easy to learn. Like, it's an afternoon for you to learn this. We should do that with sophisticated visualizations and very well-designed puzzles and games that lead you through it. It should be a very sociable experience, kids working together to solve puzzles. It should involve physical activity. Kids should be, watching their friends like play football, and like they make something that like analyzes how the football is going through the air, or they make something to try to predict where the baseball's going to go when somebody hits it with their with the baseball bat. They shouldn't be, ideally, they shouldn't be what we are now, which is reliant on apps and, software developers, these rather arcane people, pay stupid amounts of money to make all of the software for us. We should be making it ourselves. It should be very, very quick to say, oh, do you know what? I need something to do this for me. I'm going to go, blah, 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 and now I've got it. Now I've got the visualization that I'd like.
And your horizon for this is 20 years?
Sure.
All right.
You taking bets, Quinn?
I'm just penciling in a calendar invite for 20 years from now so we can check.
So I've given myself 7 years for my current project. I've done 1.5 years of it, like I say. At the end of this project, I want it to be the case that you can learn geometric algebra in this way. If you want to learn geometric algebra, as in, or apply it to making some basic visualizations. It's not that I can do any kind of visualization, but I can do some limited kinds of visualization. Let's say that you want to make a 3D version of Pong, or you want to make a little game about juggling, for example. You can use the thing that I'm making to do that, and you'll do it using geometric algebra. Do
you think you'll market it to schools?
Yeah, probably, but I'm not sure. Mm-hmm. Because I need to make it first and then figure out exactly who I can target it to.
I guess the alternative is just give it direct to the students.
I'd certainly like to do that, yes.
YouTube University.
Mm-hmm. Mm-hmm. I don't know. The world might be things might be very different in 7 years. Probably there will be some virtual reality platform that lots and lots of people are using, created by Apple, and I'll have to put it on that and sell it to whoever's using that platform the most.
Well, in the meantime, if you need testers to see how it works, we're here and willing.
Sure. I'll bear that in mind, and I probably will need some testers, yes.
Excellent.
Well, thank you for joining us, Hamish. It's been fun.
Lovely to be here.
And then where can people find you?
Oh, you can find me Hamish_Todd on Twitter. My personal website is hamishtodd1.github.io. I've just made a game. It's a visualization of something called prediction markets. It teaches you prediction markets. It teaches you Bayesian updating. It teaches you probabilistic thinking. It's a little game where you can sit down with some friends and watch a murder mystery TV show, and you're buying and selling bets on who you think did it. And this is buying and selling bets on what you think is going to happen is another visualization that I think is going to be quite useful in future. So yes, that's Twitter, hamishtodd1.github.io, murdershebet.com. And you can also reach me at hamishtodd1 at gmail.com.
Awesome. We'll put those in the description too.
Please. All right. Very, very nice to meet you both.
Bye.
Yeah, have a great rest of your day.
See you later.
Bye.